Okay, here are some of the common questions on lesson 9.3. This lesson had quite a bit thrown into each other with solving 3 different main types of problems. So they were all mixed together. And you know that's the way it's going to be in real life, so you have to deal with it and be able to figure that out. Okay, so evaluating a common log, we know from the change of base formula that this would be log 7 divided by log 3. And so you would put that in your calculator just that way, making sure you're closing that parentheses after you put those logs in, and then you get 1.7712 on this problem here. So I'm not going to give you the answers on those other ones right now, but I will go down to number 6. Okay, so number 6. I asked myself, where are the variables located? And so the variables are located up in the exponent. So how can I get the variables down? I can get the variables down by logging both sides. So I'm going to take the log of both sides. So that gives me 2x plus 3. Well, actually, let me go ahead and not do 2 steps in one. Let me write this down exactly. We got log of 2 to the 2x plus 3 equaling log 3 to the x. Okay, so now the power property of logs says that these exponents can come down in front. So this exponent can come down in front and multiply. So that will be written as this. 2x plus 3, put that in parentheses since that's a compound term. Multiply it by log 2 equals x times log 3. Okay, now, you got at this point several choices of how to solve. You could figure out what log 2 is as a decimal and distribute that. Usually what I like to do is divide away from the term that has 2 terms. I'm going to divide both sides by log 2. And so that makes this cancel over here on the left, leaving just 2x plus 3. Cross out this number 9 here. So then what I'm going to do is figure out what this is as a value with my calculator, and I'm going to say, okay, I've got log 3 divided by log 2, and there I go. I've got a value of 1.585x. And this has a value of 1.585. And you round it 4 decimal places. So then I need to get my x's together. So I'm going to choose to, at this point, subtract this 2x over and get it with these x's over here on the right-hand side. So that says 3 equals whatever that 1.585 minus 2 is, and that's 0.4150. And then I'm going to divide by that 0.415. And so x is whatever that value is. 3 divided by that previous answer, negative 7.22, not sure what I got there, negative 7.2289. Okay, so that's number 6. Now, again, does this need to be checked up here in the problem? The answer is no. I do not have any extraneous solutions. I have a problem where my variables are in the exponent. And since my variables are in the exponent, my domain is going on forever and forever in both directions. Therefore, my domain is all real numbers. And as long as I get a real answer, which negative 7.2289 is a real answer, it's not imaginary, then I'm okay. Alright, let me erase some of this, and we could do number 9. Now we'll just do number 10 instead, since I've got stuff written all over number 9, so let's do number 10. Number 10 is interesting. It's similar to number 9 in that the most common mistake that happens is this. People get all excited and they say, oh, I have a variable up there in the exponent. Ooh, and I have an e, so I need to take the natural log. And so then they start doing this. Do not do this. This is wrong. Demonstrating the incorrect way. And then they say, okay, 3x minus 2, natural log of 12e equals natural log of 8. Now let me explain to you what's wrong about that. What you have just told me is that both 12 and e have that exponent 3x minus 2. And that is not what this problem is saying. This problem is saying only the e has the exponent. So you have to isolate that e to the exponent before you can take the natural log. So do not take the natural log of this whole side. Instead, you have to get rid of that 12 first. So I have to divide by 12 first. And I get e to the 3x minus 2 equals 2/3. Now I have a term which by itself has the exponent, and now I can log both sides to bring the exponent down. So now I can take the natural log of both sides and bring this exponent down. So that's 3x minus 2 to the natural log e equals natural log of 2/3. Okay. Now we had talked about last section what ln e is. You remember what this is saying? This is saying, as an imaginary e, because the base to a natural log is this understood imaginary e. That's saying e to what power is e? Okay, remember that's 1. So this ln e has a value of 1, and it's essentially not something that I have to worry about. I don't have to divide by ln e because it's just got a value of 1. Okay, so, but I do have to figure out what this value of natural log of 2/3 is, and the natural log of 2/3 is negative 0.4055. And so 3x minus 2 equals negative 0.04055. Add that 2 over and then divide by 3. So now I'm just doing regular algebra 1, solving 1.5945 divided by 3. And my answer is 0.5315. Do I need to check it? My variable wasn't an exponent. No, I do not need to check it. I can rewrite this answer over here so I can do the next problem. Okay, does not need to be checked. Alright, now let's do number 11. This is a problem where the variable's in the base. So, what I'm going to do is first isolate this portion that has this exponent, isolate this variable by dividing by 3 first. So x to the 3/2 is 9. And so the way to get rid of an exponent, that's a fraction, is raised to the reciprocal power. Don't say multiply by the reciprocal. Raised to the reciprocal power. Raised to the reciprocal power. Don't say multiply by the reciprocal. Raised to the reciprocal power. So when I raise this to reciprocal power, the power multiplies, and that becomes 1. So I have x is equaling 9 to the 2/3 power. Okay, well, I first kind of try to do this by myself, do this without a calculator, because I know that this is my power and this bottom number is my root. So I'm thinking this is saying 9 squared and the cubic root of that. And so I'm thinking, okay, is there a cubic root of 81 or a cubic root of 9? And this doesn't come out evenly. So you should always see if you can't do this in your head, because a lot of these do come out evenly. But since this one doesn't come out evenly, then I'm going to go ahead and let you use a calculator on this one. And the way that you would do that is this. You would say 9 to the 2/3 power. Put your fraction in parentheses. 9 raised to the 2/3 power. And indeed, that isn't evenly, it doesn't come out evenly. It's 4.3267. Okay, so that's the end of that first page. Next, this page has got logs. Most of the time on this page, your variable is located here within the log. Okay? Your variable is located within the log, and let's think about what's happening. This is a logarithmic equation. Here's a graph of a log, and I know that my graphs of my logs have got asymptotes. I have a limited domain. My domain of this one is 0 to infinity. Because I have a limited domain, my answer is falling out here. I have a non-real answer. So, the moral of this little bitty side story is, if your variable is located within the log, because you could have these imaginary solutions on all of these ones where the variable is within the log, you must check for extraneous solutions. Okay, and it's not that big of a deal. You don't have to show me that work. You can just quickly go put your answer up there within the log and see if you get something that's positive, and if so, you're good, and I'll demonstrate that for you. But on these, where the variable is in the log, you have to check, because you have a limited domain. Okay. So let me erase all of this mess, and then we'll solve some of these problems. Okay, so here we go. We're going to start with number 13. We've got a situation where we have just got a single log. We have some of these other ones that have logs on both sides. Number 19, 20, 21, they have single logs. A single log, we want to isolate that log. It would not really help you to put this 8 as an exponent, and you might be tempted to do that because you know the properties of logs. But I'm going to divide by that 8 first. So I have a single log, which equals 2. Now, here's the deal. You need to remember this and put this in your brain, and remember, if you have a single log, the way to fix it is to change this into exponential form. So what does that mean? To change it into an exponent. So the little bitty imaginary understood base of this, 10. Log base 10. So what is it saying? 10 to the second power, and see where I'm getting this 2, to the second power equals x. Therefore, x is 100. Check this. It's within the log. The simple way to check it, just mentally go up here, put that within the log, 100 in the log, that's good, that's positive, good to go. It checks out. Fine. Okay? Now, on number 15, in 14, 15, 16, 17, and 18, all of them have this same situation happening. So let's just do number 17. So with number 17, we end up with this situation. See how we have these same logs on both sides? You have a single log on the left, a single log on the right, and they're both the same base log. Then what happens is, in essence, what you're really doing is just like, I'm going to raise them. I'm going to do 7 to that, and then it ends up making things cancel. But in essence, what really happens is you have same bases, therefore I can set these inter terms equal to each other. So, you know how when you have like bases, your exponents are equal. Okay, so that's saying 5 minus x is equaling 3x. And then I just solve with regular old algebra 1. So x is 5/4. Okay, now you have to check this. The variables are within the log. So I'm thinking 5/4 is my answer. I'm going to go check this. I'm going to put it within here. 5 minus 5/4, that's just 5 minus 1.25, so that's going to give me a positive, so it's fine there. 3 times 5/4, okay, of course that's going to be positive, so that checks out. See, I'm just going to go try it out, physically put it into each one of those logs and make sure it checks, and it's fine. So this one is a sample of if you have the same base on each side, you can set your, just the same way that you set your exponents equal, you can set those inner terms equal and solve. Okay. So let's go down and do number 22. The rest of those ones are pretty much the same. Don't forget that like on number 21, you have a single log. You have a single log, you have to write it in exponential form. The understood base here is e. So that's e to the 0 power equals 1 minus 5x. So 1 equals 1 minus 5x, and then you finish solving. Okay, but let's go down to that number 22. Like I said, we're gonna, that one seemed to be one I got lots of questions on, so here we go. Okay, my variable's up in the exponent, so this is like the first page. Isolate this term, which has the exponent. So I'm going to add 3 to both sides. And I get 2 e to the 2 minus 3x equaling 14. I am not taking the log yet because I have not isolated my base with the exponent. 2 does not have that exponent, so I have to divide by the 2 first before I take the log of both sides. Now I'm going to take the natural log of both sides to pull that down. So that ends up making it a compound term, a 2 minus 3x ln e equaling ln 7. And then what do you know about ln e? It's 1, the number 1. So I have 2 minus 3x equaling the natural log of 7. The natural log of 7 is 1.9495, 9459. Subtract the 2, divide by negative 3, and you're done. I'm not going to finish that one out for you, but I will tell you that you get positive 0.0180 for this problem here. Now, you have to check it. your variables within the exponent. So no, it doesn't have to be checked. If your variables within the exponent, no. Now, 25, you could do that same way, but I will tell you that there's actually a simpler way, and I hadn't thought about this except for one of my students said this. And so I love learning from my students. They recognized, several of them in my 4B class recognized that these bases could be made to have like bases. So I could make them base 6, and that's because 216 is 6 cubed, and I could raise that to the 2x minus 1 power. 36 is 6 squared, and I could raise that to the 4x plus 3 power. So then, what do powers of powers do? They multiply. So I'm going to distribute my multiplication, and I have 6 raised to the 6x minus 3 power, equaling 6 to the 8x plus 6 power. Now that I have like bases, what can I do with those exponents? I can set them equal and solve. And I'm not going to finish solving it out there, but that gets you going. Then you can finish that out. Okay. This last page has got quite a few things on it that I want to touch base with you on. Because there's condensing involved, multiple things going on here on this page that we need to address. So if you need to stop, take a break, and finish up those other problems, fine. And then when you get to this page, then come back here at 21, almost 22 minutes, and work on this page. Okay, so here's the deal. First of all, I'm going to start with 29. And I'm not going to finish all of these problems for you, but I'll kind of talk you through how to start them. I see that on number 29, I have a single log on one side and a single log on the other. So therefore, you can raise them up and set the exponents equal. So then I've got 2x squared minus 3 equaling 9x minus 13, and I can solve. And there you go. You can solve that. You're going to have a quadratic. You're going to need to check them both because your variable was within the log. So you get 2 answers, and you do need to check them both. All right, so I'll stop there. Now, look at number 28. Go back to 28. I see that I have a single log on both sides, so that's all good, but I have this 2. So how can I address that 2? Dividing by 2 isn't going to do me any good because that's just going to place it over there on that side, on the other side. Well, here, I'm going to put this up in this exponent location. So then that means that I have log base 7 of 1 minus x squared equaling log base 7 of 7 minus x. So now that I have these log with the same base, a single log with the same base, I can set my inner terms equal to each other and solve. Okay, so you're going to end up having to FOIL, and you get a quadratic, and you're going to get 2 answers, and I will tell you, one of them won't work. You need to go through this process. Let's just do that because we haven't come across any of them that don't work yet. But when you do that, you end up getting 3 and negative 2. So I get 3 and negative 2. Now, the interesting thing about this problem is, first glance you think, oh, the negative 2 is not going to work. So I know that's extraneous. Okay, so I know it's because it's negative. Well, you have to put these back into the log. So watch this. I'm going to check this 3 out by putting it in here. Well, what's that saying? 1 minus 3. That's negative 2. Can I have a negative 2 within the log? No. That is why the 3 is actually extraneous. If I put this negative 2 within there. I get 1 minus a negative 2. Well, that's actually positive 3, so it's all fine. 7 minus a negative 2. Well, that's 9, so it's all fine. So negative 2, interestingly enough, is the one that checked out. Positive 3 did not, because of the way that the numbers were arranged within the log. Okay. Now, I don't want to do all of these problems on this page, but there are some things that I need to address. And number 30 is definitely one that students made common mistakes on. Because we talked about how, oh, look, they all have log base 2. Number 30 says, oh, they all have log base 2, so I can just say this. Now, this is wrong, but this is kind of the thought process that went through students' minds. They thought, oh, I can just say x minus 3 plus x plus 1 equals 6x minus 18. Okay. And that is wrong, because you cannot set the logs equal unless you have a single log on each side. And I've been saying that throughout this log scenario. So, how can you get this left-hand side to be represented by one single log? The vocabulary for that is condense. Condense. So we're going to condense this left-hand side so that we get one single log. And when they are adding, what do my inner terms do? They multiply. So this is one single log represented by log base 2 of x minus 3 times x plus 1 equaling log base 2 of 6x minus 18. And so, guess what? Now I have a single log on both sides, and so now I can raise those up and eliminate the log base 2. So I get x minus 3, x plus 1, equaling 6x minus 18, which is going to give you a much different answer from before. So, when you saw that, you will get two answers. One of them will be extraneous, I'll just tell you that much. You're going to have to FOIL this and factor and all that good stuff. Okay. I think that's probably all that I want to address on this page. 33 and 34, similar to the front in that you've got your variables up there and the exponents. 32 is interesting because we didn't quite know how to address this double minus. So let's kind of start 32 and then we'll finish that. Not finish that completely. Okay, so I can tell that I've got multiple logs here and I'm going to need to condense them. That's the vocabulary. So I'm going to condense them. So if I condense these first two, that's going to be saying log base 2 of 7x minus 8 divided by x plus 1. Okay, no problem there. But what happens when you divide by this next one? So I'm taking 7x, let me write this out to the side so you can see clearly what's happening. Taking 7x minus 8, dividing it by x plus 1, and then dividing that entire result by your x minus 1. Well, when we studied complex fractions, we know how to address this bottom x minus 1 by multiplying by the reciprocal. Multiplying by the reciprocal. And so where does that end up putting this x minus 1? On the bottom with the x plus 1. So do you see that? So 7x minus 8 was divided by both the x plus 1 and the x minus 1. And that equals 1. Okay, and I'd like to stop there, but based on how I know my other students have done, then they kind of get stuck. So look, you have one single log. Do you remember what I said you have to do when you have one single log? One single log, you have to write it as an exponent. So that's 2 to the first power is equaling this 7x minus 8 divided by x plus 1 times x minus 1. And then you can go on from there. And so that's saying 2 equals 7x minus 8. I'm going to FOIL this. I know I have a difference of perfect squares, so I've got x squared minus 1. How do I get rid of that x squared minus 1? I'm going to multiply by x squared minus 1 on both sides. So then you would multiply both sides by this x squared minus 1 to get rid of that base down there. So 7x minus 8 is equaling 2x squared minus 2. And voila, we have a quadratic. You're going to have to solve. You're going to have to factor. You'll get 2 answers. You need to check them both. All that kind of stuff. I think that's it. But you know what, though? I was just thinking there was one very interesting thing on number 30. I will tell you that you do get 2 answers. One of them ends up being 3. One of the answers ends up being 3. When you do your FOIL. Now this is interesting. Plug this in to see if you have something extraneous. I'm putting that 3 in. And that is 3 minus 3. And what does that make within the log? 0. Are you allowed to have 0 within your log function? Our asymptote is at 0. It's approaching 0, but never going to reach it. 0 is not included. The domain is from 0 to infinity, but not including 0. So 3 was really, really, really close, but still extraneous. Okay, and then the last page is just our matching. Remember that you have to graph the corresponding exponential function. So I don't recommend graphing the log. Remember what this is saying here. 3 to the y power equals x. Well, what's its inverse? Switch the x's and y's. That would be 3 to the x power equals y. We can make a table of our inverse much easier than we can make a table of the log. I'm just going to put in 2 numbers here. 3 to the 0 is 1. 3 to the 1 is 3. So this is the table of my exponential function. This is my exponent table. How do I get back over here to the log table? Switch your x's and y's back. So that makes my log table to be the inverse of that other table, which would be 1, 0, 3, 1. And so that is then the way that I can go and find my first initial graph, 1, 0, 3, 1. I think that's like this one. 1, 0, 3, 1. Okay? Alright, so there's all of the help for the examples, or for the lesson 9.3.